Hey everyone, in this highlight video we're going to learn about molecular representations, or in other words, how do chemists draw organic molecules. Alright, so there are three types of drawings that we will see in organic chemistry. The first is called a condensed structure, and this is essentially what we could draw if we were using a keyboard. So it would be something like CH3, CH2, CH3. So it's all in a line with subscripts telling us how many of each of the atoms we have. We may see condensed structures that have parentheses, and those parentheses tell us that the group that's in the parentheses is attached to the atom to the left. So for example, we could have something like this, with an OH there, and maybe another parentheses over here. Alright, so these parentheses here tell us that this OH is attached to the carbon that's to its left. The parentheses here tell us there's two of these CH3 groups both attached to this carbon right here. Alright, so this approach is fine for simple molecules, but it's not very good if we're going to draw very much more complicated molecules. The next type of drawing are Lewis structures, and we've already seen Lewis structures. Essentially, in these structures, we use lines for bonds. Usually, if we draw a full Lewis structure, we're going to draw the non-bonding electrons, but sometimes we'll skip drawing those if they're not really necessary. So examples of Lewis structures for the structures above, we could have drawn out all of the bonds like this. Alright, so this is propane, the same as this molecule up here. If we wanted to draw the molecule up on the upper right, it's going to take us a little more time. We see that that carbon right there has a H and an OH attached. Alright, and notice that this carbon right here has two CH3s just like this one did up here. Alright, so Lewis structures, we could draw more complicated structures, but it takes so long, right? We've got to draw out every bond. So that's really cumbersome. So we've got a better way to draw organic structure, and that involves what we call skeletal structures. And these are very much more simplified. So the first things that we do in drawing skeletal structures is we omit the carbons, so we don't even draw the carbons, and we don't even draw the hydrogens as well. All right? We can identify where the carbons are because they're assumed to be at the ends of the lines and at the junctions between lines. Finally, we have as many hydrogens on the molecule as are assumed to complete the valence for carbon. Right? So we already learned that carbon, when it's neutral, it has 4 bonds. So for each carbon in the molecule, we won't draw in the hydrogens, but we'll know that they're there, and enough of them to add up to 4 bonds per carbon. So a couple of examples out of the book here. So this is a hexane. Hexane in its Lewis structure up here has 6 carbons, and it's drawn out all the hydrogens to give it 4 bonds to each carbon. So if we were going to draw a skeletal structure here, all we would need to do is draw a zigzagging line like this that has a carbon on the end and on this end, and a carbon at each junction between the lines. All right, so we have 6 ends or junctions, and we would assume for a position here on the end that shows only 1 bond back to the other carbon. So in order to have 4 bonds, it has to have 3 hydrogens. So that's like the CH3 here. The ones in the middle show 2 bonds from this carbon over to this carbon and to this one. And so there's 2 bonds. It needs 2 more bonds, and so it has 2 hydrogens. All right? So this is a straightforward way to draw structures, but it takes some practice. And you want to make sure that you understand really what these skeletal structures mean. So let's try a problem. To get a little more practice, let's convert some skeletal structures back to Lewis structures. Okay, so in each of these cases, we're going to start with a skeletal structure over here. And we're going to convert it to a Lewis structure. All right, so take 2 steps. We won't always have to do these 2 steps, but formally, the first step is to add in the carbons. All right, so we're going to draw this same skeleton on the left, but we're going to explicitly draw out the carbons. Okay, so we can start on this carbon. We have our ring. And then we have these groups down here. All right, so that shows all the carbons. Let's put in our OH over here. All right, so the second step is then to add hydrogens and lone pairs. So we have to add enough hydrogens to give each of those carbons 4 bonds. So let's just go ahead and draw the carbon skeleton first. And then I will add all of the hydrogens. Okay, there's all of the carbons. All right, so this one up here only has 1 bond, so it needs 3 hydrogens. So it needs 1 hydrogen. This needs 2. This needs 2. Wow, wasn't that fun? See how slow that is to draw the Lewis structure. So that was all the hydrogens. So let's add in some lone pairs. Where would we need some lone pairs? Okay, the only place we'd need lone pairs is on this oxygen, and we'd have 2 lone pairs. Okay? All right, let's do one more. First step, add carbons. Okay, so we make sure that we have all the same lines. We just put carbons at the ends of the lines or the junctions. So one tricky part for this triple bond is to remember that there's a carbon right there and a carbon on the end. All right, second step, we're going to add hydrogens. We can just redraw this carbon skeleton, and then we can add our hydrogens. All right, is that good? Nope, missed one right there. All right, so there's all of the hydrogens on that molecule. Do we need any hydrogens on these? No, because that carbon has a triple bond, so that's 3 bonds plus 1 bond to hydrogen, 4 bonds. That's all we want to give each carbon. All right, let's do one last one. Okay, so we have another ring. Okay, this ring has an oxygen on it. That oxygen has a carbon and another carbon, and a double bond to an oxygen. And over here, this one's a little tricky, carbon with two oxygens. So that's going to be like this. The Lewis structure for that kind of group has one oxygen with a double bond, the other oxygen with a single bond. All right, so there's all of the carbons and oxygens. So the next thing we have to do, let's draw in the double bonds over here though. Next thing we have to do is to draw in the hydrogens. And I'm just going to go ahead and draw them in on the same molecule. Let's do these in blue. Up here, this carbon has 1, 2, 3 bonds, so it needs one hydrogen. This one needs one. This needs one. This needs one. This one here already has 4. The one above it already has 4, so those don't need any hydrogens. And we just have to put 3 out here. All right, so all of these, they're really cumbersome to draw. This last structure is an interesting one, though. This is the structure of aspirin. Let's do one more problem. All right, so a few little tricks to drawing skeletal structures as well. So what about when we're drawing heteroatoms? So heteroatoms are atoms other than carbon or hydrogen. So oxygen or nitrogen or chlorine or bromine, things like that. So we're going to draw out all heteroatoms. All right? There's no shortcut to those. We have to draw them out. We need to draw out all of the hydrogens that are attached to heteroatoms. So for example, if we have an OH, we need to draw, if we have the O, we have to draw the H on it. Okay, so we don't draw something like this, all right, and leave the hydrogen out. It's just basically uncool. Okay, we don't do that. Lone pairs can be left out, all right, but you can't forget that they're there, because sometimes we need to use them. When we start drawing chemical reactions, we're going to need to know when they're there. So basically what we do is we draw them out when we need them. The last thing is that we can use the formal charge, and I'll talk about this on the next slide, to determine the number of lone pairs that there should be. All right, so let's look at charges. Here we're going to look at charges on carbon atoms specifically. So if we have a charge on a carbon atom, that charge is going to replace one hydrogen. So if we have a plus charge like this, that means that that carbon, which would usually have 2 hydrogens attached, now only has 1 hydrogen. If that carbon down here has a minus charge, likewise, whereas a carbon like that would usually have 2 hydrogens, this one only has 1. Then we can determine the number of non-bonding or lone pairs from the charge. If that carbon is positively charged, then it has no lone pairs. So that's like this, no lone pairs here. So this is called a carbocation. All right, and that carbon has only 6 electrons around it. Down here we have a minus charge. If that has a minus charge, that means we need to add 1 lone pair. This is called a carbanion. Okay? Finally, look at a few things that you need to do if you want to be a cool organic chemist. First off, do not mix up Lewis structures and skeletal structures. Okay, those types of drawings. All right, so if we have a molecule like this, let's go to butane, is 4 carbons. Okay, we can draw the skeletal structure for this. So I would start counting at the end. So that's 1, 2, 3, 4. All right, so this is butane. But what we don't do is we don't do what we were doing as a step in between. We don't draw this like this with no hydrogens attached. All right, so if we're going to draw the carbons out as C's, we need to add the hydrogens. All right? The second thing up here is that we should try to draw the bond to the correct atom. All right, so if we have a molecule that's like and we're going to draw this in a skeletal structure, then we have the oxygen, we have 2 carbons, and we want to make sure to put the H over on this side. So the point that I'm making here is that this bond here goes from the carbon directly to the oxygen. Okay, so what we don't want to do, and it's a common mistake, is draw it like this, like an OH, okay? Because that puts the hydrogen in between the carbon and the oxygen, and we just know that that's not the way it is, okay? So that's not so good. Finally, well, let's just draw another one. Drawing it to the correct atom. Let me show you one more example where I've seen things like this. Okay, so let's say we have an NH2 group. Okay, and I'm going to draw it like this. Okay, so notice I've drawn the bond from the carbon to the nitrogen. We would not want to draw that just in the middle of this group, right? Because the bond doesn't go to the NH2 group, it goes to the nitrogen, and the hydrogens are attached to the nitrogen. Okay, so that's not good either. All right, the last thing is, and you've probably seen this, and this is what I've actually done up on the top up here, is that when we draw carbon chains, we draw them as zigzagging chains. So here we'd have 2, 3, 4. All right, so how many carbons are attached to that? All right, so we would have 1 on the end, 2, 3, 4, 5, 6, 7, there would be 8 carbons. All right. How many hydrogens are attached? C8. We have this carbon on the end. Number 1 has 1 bond to carbon 2, so it has to have 3 hydrogens. So 3 carbons, 2, 3, 4, 5, 6, and 7 all have 2 carbons, 2 hydrogens each, so 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 8 has 3, 18. H, 18. We'll learn in the next chapter, or maybe in 2 chapters, that the reason that we draw this in a zigzag like this is because it's the best way to simulate the correct bond angles between those carbon atoms. All right, so let's try one final problem. Make sure to keep practicing all of these different drawing approaches so you become very comfortable with them. We're going to be using this throughout the next 2 semesters of this course.